Good evening, class. We are going to look at the last section of Chapter 11, Section 7. It's time to look at probability and geometric probability. Remember, probability is the likelihood an event will occur. If it's going to be a certainty that it will occur, it'll be a 1. And if it's never going to happen, and it's an impossible event, it'll be 0. Now, any probability has to be within that range. It's either going to happen, not going to happen, or somewhere between. For probability, it's not going to be so certain that it's going to happen twice. No, we're just going to look at, is it going to happen, is it not going to happen, what's the likelihood of that to be. So our numbers for probability will always be between 0 and 1. Now for the most part we do probability of, and we put it in parentheses there. Don't get this confused with perimeter. Sometimes we leave this as a capital P. Now, to find probability, usually probability is represented as the spot it could be or we're interested in, or the region that, or the event, or whatever we're looking at. And this is the number of possibilities of where we could choose it from, or possibilities. Alright? So it's always a ratio that will involve kind of like the region or the event that we're looking at specifically, and then over all the possible things that could happen at that point. So for us, when we talk about geometric, we're looking at length over length. So like the length that we're interested in over the whole length we're choosing from. So for instance, in this picture here, if I would look at that number line, if I would choose from anywhere on that number line, from A to B, what's the likelihood it's on segment CD? Well, that's the length of segment CD divided by the length of AB. That's how likely it is that a randomly chosen point is on segment CD. So, using these words up here, it says, let segment AB be a segment that contains the segment CD. If a point K is chosen randomly on the big segment AB, then the probability that it is on segment CD is going to be the ratio of length of CD to the length of AB. So what is the probability that it's on segment CD? Well, that's going to be the length of segment CD to the length of segment AB. So the probability that it's on the length of segment CD in my picture over here is going to be the length of segment CD. Well, it goes from -3 to 1, so 1 minus -3 is 4, so the length of segment CD is 4. Segment AB goes from -8 to 9, so 9 minus -8 is 17. So the probability that it's going to land here is 4/17, or, when plugged into a calculator, 0.235. It has a very low likelihood of happening. It's more likely not to happen than it is to happen. And that's what this is for. We're just trying to see the likelihood of an event happening over a certain region. So, here's example 1. If I was going to ask you, find the probability that a point chosen at random is on, and I give you 3 options. I messed that up. It's supposed to read, find the probability that a point chosen at random on segment AB is on blank. So this segment AB and this blank is supposed to be switched around. So what's the probability if I choose a point at random on segment AB that it's on each of these 3 segments? So yeah, I messed up my phrasing there. So essentially what I'm trying to find is 3 probabilities. The probability it's on segment AC, the probability that it's on segment CE, and the probability that it's on segment CB. Alright, so if I'm choosing at random on segment AB, which I know I've used an abbreviated for it here, I know that the probability is going to be over whatever the length of segment AB is. So for each of these cases, so the probability of, let's just say, it being on segment AC is going to be over the length of segment AB. Length of segment AC over length of segment AB, well, it's just counting the length in this case. Length of segment AB, well, 9 minus -7 is 9 plus 7, or 16. So length of segment AB is 16. Length of segment AC, negative 3 minus negative 7. Well, that's negative 3 plus 7, or 4. So the probability that it is on segment AC is going to be 1 to 4, or 0.25. It's not very likely of happening. Now, if I would look at the probability for segment CE, I'm going to erase this part here, and I'm going to fill it in. So CE is what I'm looking at. Now, the length of segment AB hasn't changed. It's still 16. So I know the bottom's still 16. But now I'm looking at length of segment CE. So segment CE is from negative 3 to 5. So 5 minus negative 3, 5 plus 3 is 8. 8 divided by 16 is 1/2, or this has a probability of 0.5. It's just as likely to happen as it is not to happen. Alright, and for the last one, again, 16 is on bottom because I know the length of segment AB is 16. Well, the length of segment CB is from negative 3 to 9, so I do 9 minus negative 3, or 9 plus 3, and that's 12. Reduce that, and I get 3/4, or 0.75. So this has a likelihood of, it's likely to happen. 75% is a good grade. This has a good likelihood of happening. Alright, and there we go. That's basically it of the non-applied side. But if I would look at this in application, I could look at it in this situation. What if I had something like a monorail runs every 12 minutes? You know the ride from the station near your home to the station near your work takes 10 or 9 minutes. You've timed it out. You know it takes exactly 9 minutes long. Well, one morning, you arrive at the station near your home at 8:46. You want to get to the station near your work by 8:58. What is the probability you will get there by 8:58? Well, if I look at the number line. Now, a monorail arrives every 12 minutes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I need a little bit more. All right, it arrives every 12 minutes. So this is when it has a chance of arriving for you. Now you know it takes 9 minutes from your place to work for this monorail to get there. And you want to be at work at 8:58. And you arrive at the station at 8:46. Well, that means you want to arrive at the station 12 minutes from now. But it takes 9 minutes of travel time to get there. So what you're wondering is the likelihood that it'll arrive by no later than 3 minutes after you get there. So that it'll arrive no later than 8:49. Because then you'll get to the station there and you'll be right where you want to be. What is the probability? Well, the probability that it lands somewhere on this segment in the first 3 minutes, the probability that it will land on segment AC, is going to be the length of segment AC to the length of segment AB. In this case, 3 minutes to the 12 minutes between times it stops. So the probability that it's going to arrive is 3 divided by 12, or 0.25. The probability is that it's not very likely that it will arrive in the next 3 minutes. Hopefully you plan out better next time. So yeah, you can apply it to stuff like this, where you're looking at different lengths of time, and you apply it to a number line and you use this probability. It's not just for geometry. You can use it for other things. Now, there's another type of probability we can look at. Maybe we're not just going to be looking at lengths. Maybe we'll also look at areas. Now, where could this be used? Maybe you are searching for a lost person. and you know you can only cover region M amount of space. But they could be anywhere in J. If I choose at random, they're somewhere in J randomly. What's the likelihood we're going to find them? So that way I might not be discouraged that I don't find them the first day, but maybe find them the second day because the search area wasn't big enough for the first day. Well, here's how we find the probability. Let J be a region that contains region M. If a point K is chosen at random in J, then the probability that it is in region M is the ratio of M to J. So the probability that it's in region M is going to be the area of region M divided by the area of region J. That's it. That's all it's saying. So again, we're going to take the area I'm looking at or hoping for, and we're going to divide it by the total area it's over. So let's look at an example problem. What if I asked you to find the probability that a randomly chosen point is in the yellow shaded region? Well, if I want to know the likelihood it's here, I have to find out what the area of that region is. Oh, to find out that area, if I knew the area of the square and I knew the area of the circle, I could subtract them to get the area of that shaded region. Because the big area minus the small area would be the area left over. So the area of the square is going to equal the side squared. So 16 squared. So the area is 256 for the square. Unit squared. Now the area for the circle is pi r squared. Pi times the radius isn't 16, it's 8 of the circle, because if the full length is 16, then half is 8. So area equals 64 pi, or 201.06 units squared. So this is the area of the circle. Now the area that I'm interested in is the difference of the two. So 256 minus 201.06 is going to be 0.94, I know that. 54.94 units squared. Now the probability that it's in the shaded region, so I'm going to say probability of Y, yellow shaded region, is going to be 54.94 units squared divided by 256 units squared. So let's just take a look. I just said that the probability it's in the yellow shaded region is the area of the yellow shaded region divided by the area of the whole spot I'm picking from, which is a square. So 54.94 divided by 256. At this point, it's a calculator problem. 54.94 divided by 2. The probability it's in this yellow shaded region is 0.215. It's not very likely. Alright, there's 2 more to go. I'm going to put 2 up here, and then 3 I'll also put up here, but I'll be asking you to do that one. Alright, so they want this outside region of the circle. So if I want to find the area of the circle, that would just be pi r squared. In this case, that would be pi 4 squared. So the area of the circle, the big shape, the shape that I'm going to take it out of, is 16 pi, or, because it's a probability one, I think it might be best to just enter it in the calculator right away. 16 pi is 50.27 units squared. Now, I already know part of my probability. The probability that it's in the yellow shaded region is going to be something out of 50.27. Because that's the total area it could be. The circle is the biggest area. Alright, so now I need to find the area of the square. Oh, wait a second. Area of a square, well, a square is also a rhombus. So the area of the rhombus that I see here, the square, which is not labeled, but it is a square, is, well, in this case, it's a square. So both diagonals are congruent. One diagonal is 8, the other diagonal is 8. So 1/2 of diagonal 1, 8, times diagonal 2, 8. So the area of my rhombus is going to be 1/2 of 64, or 32 units squared. The area of the yellow region is going to be equal to 50.27 minus 32. So the area of the yellow region is going to be 18.27, and that's what I'm looking for, 18.27. So I found the area of the circle, I found the area of my square or rhombus, and I took the difference of the two because I was only looking for the area of the yellow. Not the square, not the circle, but the I take that, divide by the 2, and see what I get. 18.27 divided by 50.27. And I get the probability it is in the yellow region is 0.36. Again, not very likely. Alright, there's one last example on this slide. See if you can do it yourself. Alright, if you did it correctly, you should have found the area of the rectangle to be 40 units squared. To find the area of the triangle, you had to know this was 10, and then you had to use Pythagorean's theorem. A squared plus b squared equals c squared to get x equals 12. Then you plug that into the area formula for a triangle, you get 60 units. In this case, because I did the area of a rectangle, area of a triangle, the area total is going to end up being the addition of the two because there was this here. It's the whole thing, not just the triangle, not just the rectangle. So when I do the probability, it's this shaded region, the rectangle, divided by the total, 100. So the probability is 0.4. And there we go. This is pretty much, again, what we're going to be looking at. And this is pretty much all that you need to be able to do. If you've got it, great. If you don't, see me. There's one last example that we have to go over, though. And that's this case. What if I had a target? And I wanted to know the probability that if I was just throwing randomly, I didn't have any skill whatsoever, except for that I could always hit the target itself. What's the likelihood that I'll hit the bullseye? So the diameter of a target is 80 centimeters. So we're going to assume that this target is circular, so I'm going to draw a picture. Its diameter, 80 centimeters. Now, if I shoot an arrow at the target, what is the likelihood that I would hit the red circle in the middle? So if I shot randomly, what's the likelihood I hit the red circle? If the diameter is 10 centimeters. So again, I'm good enough that I will always hit the target, but where I hit on it is entirely random. It's kind of luck on what I get. So what's the likelihood that I hit the middle? Well, in this case, it's going to be the area of the red, and I'm going to take it and divide it by the area of the black. And that's the probability that I will hit the target. Right in the middle. So, to find the area of the red, I have to find the area of that circle. Pi r squared. Area of the red will be pi times, well, the radius is 10, sorry, the diameter is 10, so the radius is 5. So area equals, for the red, 25 pi centimeters squared. I'm going to leave it like that. Area for the black is going to be pi times the radius squared. The radius is not 80, but 40 centimeters. Area of the black is going to be 1,600 pi centimeters squared. What's the probability that I hit the target at random if I had no skill besides being able to hit the target every time? Well, it's going to be the area of the red, 25 pi centimeters squared divided by the area of the black, 1,600 pi centimeters squared. The pi's will cancel out just like the centimeters squared. 25 divided by 1,600 leaves me with a probability of 0.15625 that I'll hit the target. Basically, it'd have to be a really lucky shot if I did it at random to hit the center. So people that can hit the center over and over again, it's not luck. Because if it was, well, that is some extreme luck. Because this is just one arrow. But if they could do it 20 times in a row, the likelihood of that happening drops real quick. It has to be skill. But there we go. That's how you can find the probability. Find the area that I'm interested in, divided by the area total, and you'll get the probability that that event would happen at random. And that's it for probability. So you're taking the length you're interested in, divided by the length it's out of. If it's area, you just take the area that you're interested in, divided by the area it's out of. And that's pretty much it. If you can do this, you've got everything from chapter 11 good to go. This section has a lot of formulas. You're going to have to memorize all of them. And you have to remember the ones from previous chapters. So make sure you get these, memorize them, know them, and you're going to need them. Alright, that is all. Until next time.